Hello, I am Kazuki Fuji from National Institute of Technology, Tokyo College, Japan. I will now be presenting the speech perception and psychoacoustic session at ICASSP2020. In this video, I will give about the HumanGAN, which replaces a computer-based discriminator with human-based discriminator. A generative adversarial network, GAN for short, is a powerful deep generative model and consists of two models, a generator and discriminator. The generator is trained to fool the discriminator, and the discriminator is trained to distinguish real data and generated data. The finally trained generator represents the distribution of real data, for instance, a distribution of actual human voices. Here let me talk about humans' speech perception. Humans have some tolerance for media deviance. For example, a voice converted by a voice changer is not an actual human's voice, but we can recognize the humanity of the voice. Namely, we can recognize the formatted voice as human's one. Therefore, we can say that such a human acceptable distribution is typically wider than the real data distribution. Going back to GAN, the basic GAN can represent the real data distribution, but cannot represent the human acceptable distribution. In this study, we propose a new GAN, named HumanGAN, that incorporates human into the training. We aim to train the generator to represent the human acceptable distribution. The generator is trained by fooling crowd workers' perceptual evaluation. We conduct some evaluation in speech naturalness modeling and demonstrate that human acceptable distribution is actually wider than the real data distribution, and our HumanGAN accurately models the human acceptable distribution. First, let me review the basic GAN. The basic GAN has two models, a generator and discriminator. These models are deep neural networks, DNN for short. The input of the generator is a random variable sampled from a known probability distribution, and the input of discriminator is a real data or a data generated from the generator. The generator is trained to let the discriminator identify the generated data as real. The discriminator is trained to accurately identify the generated and real data. The objective function during training is shown in the middle of this slide. The black frame term is minimized in the generator training, and the red frame term is maximized in the discriminator training. By iterating them, the generator finally represents the real data distribution. The problem with the basic GAN is that when the human acceptable distribution is wider than the real data distribution, the basic GAN cannot represent the human acceptable distribution. Here, let me purpose our HumanGAN incorporating human perception as a discriminator. In our HumanGAN, we aim to train the generator to represent the human acceptable distribution. To achieve this, we replace the DNN discriminator of the basic GAN with human perceptual evaluation. The middle of this slide shows a comparison of the basic GAN and HumanGAN. The generator of the basic GAN is trained to fool the computer-based discriminator, that means the DNN discriminator. On the other hand, the generator of the HumanGAN is trained to fool the human-based discriminator, that means crowd workers' perception. The bottom of this slide is the objective function during training of the HumanGAN. The red frame term is maximized during the generator training. The term is posterior probability of the human-based discriminator. Namely, the generator is trained so that the generated data is higher rated by humans. To optimize the generator's model parameters theta g, we use a stochastic gradient descent. The theta z is iteratively updated using the gradient partial v partial theta z. The critical problem here is that human is not differentiable, as you know. The objective function v includes human perception. Therefore, partial v partial theta z cannot be analytically derived. Here, we decompose the gradient. The partial v partial theta z is decomposed into the product of partial v partial x hat and partial x hat partial theta z, where x hat is the generated data. The former cannot be derived analytically, but the latter can. Therefore, if the former is estimated in some way, we can estimate the gradient partial v partial theta z and run the standard backpropagation algorithm to update theta z. To approximate the partial v partial x hat, we utilize the black box optimization algorithm shown in the next slide. Natural evolution strategies, NES for short, is a black box optimization algorithm using perturbations. The original NES was proposed for computer-based discriminator, and D in this slide indicates the computer-based discriminator, for example, DNN discriminator. First, a small perturbation delta x is randomly generated from the Gaussian distribution. Then, the difference of posterior probabilities, delta D, is calculated using the first formula. Finally, the gradient can be approximated with the second formula. Sigma is a standard deviation of the Gaussian distribution. In this study, we apply this scheme to the human-based discriminator of the HumanGAN. In the HumanGAN, instead of inquiring the computer-based discriminator, we inquire crowd workers to obtain difference of posterior probabilities. In the example of speech naturalness variation, we present the crowd worker two perturbed speech samples, x hat plus delta x and x hat minus delta x. The crowd worker answers to how degree are two sample different. If first speech sample sounded significantly better, delta d will be plus 1. Also, if the second one sounded significantly better, delta d will be minus 1. During this formulation, the gradient partial v partial x hat can be approximated using the NES algorithm. Okay, let's move on to the evaluation. The purpose of the evaluation is to investigate our HumanGAN can represent human acceptable distribution of speech naturalness. We conducted two experiments. The first experiment confirms that the human acceptable distribution, which means a distribution we can recognize voice as humans one, is different from the real data distribution, which means a distribution of actual human voice. The second experiment demonstrates that our HumanGAN can represent the human acceptable distribution. The table lists the experimental conditions. The generated data was two-dimensional spectral parameters. The data space was obtained by principal component analysis using many speakers' value data. The data space was scaled so that many speakers' data for zero mean and unit variance. Please check our paper for the detail. In waveform synthesis, we generated the two-dimensional parameters and copied them for synthesizing 1 second waveform. CrowdWorker listened to the 1 second waveform and rated the naturalness. The DNN generator was the feedback neural network. The first experiment compared the real data distribution and the human acceptable distribution. This episode emphasizing the need for our HumanGAN. The data space was divided into grids, and we synthesized the waveform for each of the grids. We asked crowd workers how natural does the sound seem to be, and the crowd worker rated from 1, which means unnatural, to 5, which means natural. Finally, the obtained score was normalized to represent the posterior probability of each of the grids. The figure shows the result. The brighter the color, the higher the posterior probability. As we said, the real data, that mean many actual speakers data, follows zero mean and unit variance. The region, white indicates the real data distribution, and white circle in the figure. You can see that the human acceptable distribution, which means a brighter region in the figure, is significantly wider than real data distribution. This human acceptable distribution cannot be modeled with basic GAN, and we can demonstrate the need for the human GAN. The second experiment performs the generator training to see whether the generator can represent the human acceptable distribution. We perturb the sensitized waveform and generate two samples A and B and ask crowd workers which sounded more natural. The crowd worker rated from 1, which means A is significantly better, to 5, which means B is significantly better. The difference of posterior probability is obtained as listed in the table. The figure shows the generated data in each step of generator training. The white points are the generated data. Please note that we are showing the color map of the posterior probabilities of intuitive understanding, but it never uses the generator training. You can see that by iterating the generator training, the generated data moved from the darker region to the brighter one. It means that the posterior probability of the generated data are improving by the iteration. Therefore, we can demonstrate that our training can successfully improve the posterior probabilities. That is the objective function of the human GAN. Due to the time limit of the presentation, we did not show the numerical improvement, but you can find the result in our paper. Okay, let me conclude this talk. The purpose of this study was to train a DNN generator to represent human acceptable distribution. By replacing the DNN discriminator with a human perception, we formulated the generator training algorithm that involved human insight. The experimental result demonstrates that our human GAN can represent the human acceptable distribution of speech naturalness. Our future work includes to tackle the financial problem during training and cost of crowd workers' resources, not the cost of dimension. If you have any questions, please feel free to contact us. Thank you.